Okay, we'll get going. So hopefully we're going to wrap up chapter 9 today. Did I talk about perpetuity last time? Yeah, okay. So we have one more kind of concept to add. This is the perpetuity. So we've talked about an annuity, which is a fixed stream of cash flows over a period of time, over a regimented period of time. So you either get $100 every year or $1,000 every quarter, and we'll get into units below a year today, but you get it over some period of time for a fixed period of time. So $1,000 a year for 10 years, right? And I get it on December 31st every year for 10 years. So with an annuity, there is a end point, right? There is a given endpoint, that n number, letter n, that we are using to calculate the number of payments, right? There's a fixed number of payments. With a perpetuity, it is perpetual, right? So it goes on forever. So this is more of a conceptual thing than a reality, though they do in fact exist. And we'll use this formula as part of our calculations when you're valuing a stock, for example, that pays a dividend. So this is jumping ahead a couple of chapters, but when we get into stocks, there are some stocks, if you were to buy a stock, like if you were to buy HCA, Hospital Corporation of America, the company that owns Portsmouth and Frisbee and Parkland up here in New Hampshire. If you were to buy HCA, they pay a quarterly dividend, which means if you own the stock, if you are a shareholder of record, they will send you, I think it's like $1.50 every quarter. It's not a huge amount of money. But if you owned 10,000 shares, then that's 10,000 times $1.50, right? That starts to become something of some significance. Conceptually, you would evaluate. We'll use this formula to value or price the stock based on the stream of cash flows that you would expect to get from owning the stock. Now, the dividend is a thing that you expect to keep coming to you forever, right? As long as I own the stock, I should be getting a dividend from them. Now that's conceptual because, again, HCA could run into hard times and they could stop giving their dividend. But as we model it, we treat it as if, at least in some of the models we'll treat it as if the dividend is going to come forever. So if we imagine that the dividend, which we'll refer to as the payment, is say $150, right? And now we're going to imagine that we're not going to get it just one time. We're going to get it every year forever. The perpetuity formula is the present value of a perpetuity is equal to the payment divided by the discount rate, or I, right? So I, in this case, we're going to refer to as the discount rate. It's the interest rate, right? I'm going to use that again. I'm going to use the words discount rate, interest rate, hurdle rate kind of interchangeably. So just get used to me kind of bouncing between those. They all mean an interest rate. A discount rate and a discount rate specifically means it's the interest rate I'm using to bring future cash flows to the present. All right. I'm not going to refer to, if we're doing a future value problem where I'm saying how much, if I deposit some money today, how much money am I going to use get in the future? I'm not going to say, well, the discount rate is 5%, because that doesn't make any sense. I'm not bring it back. I'll be more careful. I will say interest rate, but a lot of times if I'm talking about a present value problem, I may kind of bounce between saying interest rate or discount rate. So in this case, it's the interest rate that we're going to use to value those future payments today, right? So if we were to apply a discount rate of, say, 10% to HCA based on its risk, and we'll again talk more about that, what we would say is, okay, how much would I be willing to pay for a share of HCA if the annual dividend was $1.50. So the payment was $1.50, and the discount rate is 10%. So I would just simply divide 1.5 divided by 0.1. And conveniently, if you divide by 0.1, it's the same thing as multiplying by 10. So I would say that I would be willing to pay $15 for a share of HCA. And HCA does not trade for $15, and I'm not 100% sure what the payment and what their dividend actually is. But that's the perpetuity formula. Okay, there are historical examples. Great Britain was involved in a lot of wars back in the day, with it, with France and with Spain, and and so on. And in order to raise funds to outfit their navy and army, they in some cases sold perpetuities, which were perpetual payments that you would receive from the crown. You give them some amount of money today, and they will give you some amount back forever, right? And these things were like initially created in like the 1600s or 1700s, and they ran until the 20th century. Now, they might have been like 2 cents or something like that, which was a lot of money back in 1600, but not so much in the 20th century, right? Matt. As what bonds? So these were essentially war bonds. The U.S. offered up what were mounted to treasury bonds. I don't think any of them were perpetuities. So the purpose was the same, but they weren't perpetuities. I believe, and you'd have to check me on that. I believe they were a fixed life, more standard bond. And we'll talk when we get in next chapter. I think we actually start to get into bonds. So these things were hanging around for a couple of centuries. People were collecting on them. So pretty good, in terms of conceptually, yeah, it went on for a long time. And I think they eventually whoever owned them was paid off, and they closed them out. So they used this formula to say, okay, at 2 cents per bond that you were holding, or 2 cents per perpetuity you're holding at a discount rate of 3%, we'd owe you 17 cents for each of them or something like that. And they just paid it off. I'm making up a number because I don't know the actual numbers, but I believe they finally did pay them off sometime in the 20th century. But these are mostly, the formula is useful conceptually, not so much like there aren't many perpetuities out there, but they're useful. We'll see this formula again when we go to do some of our other modeling. Okay, so you just need to know this formula. I'll give it to you, but if I ask you a question that sounds something like, Grace offers you a payment of $100 per year forever, and you value Grace's ability to pay you, or the appropriate discount rate based on what you know about Grace's ability to pay would be 14%. How much money would you be willing to pay Grace for this stream of cash flows? And you need to know, okay, well, the key words there is it's a stream of cash flows forever. Okay, that's a perpetuity, not an annuity. So Grace isn't offering to sell you a 10-year stream of cash flows or an 8-year stream of cash flows. She's offering to sell it to you forever. Now, I'm not sure how she would do that, because she's a human being, and so at some point she would have to stop paying because she's eventually going to die, but not soon. So corporations are more likely to be able to make a promise like that because they don't have a kind of natural life, whereas human beings do. So that's, you would have to be able to pick out based on the wording, oh, that's a perpetuity, as opposed to Grace is offering, would like you to lend her some money. She's willing to pay you $100 a year for 10 years. How much money would you be willing to pay her? That's an annuity, right? Because it's a fixed payment for a fixed period of time. Right? There's a fixed payment of a certain amount each year for a limited amount of time. So that's the difference between an annuity and a perpetuity. Both of them pay a fixed payment. One has a time limit, the other goes on forever. So you're looking for that forever phrasing. Okay. All right. So let's keep going. So let me ask you this. I'll throw one more at you. We have you're offered a $2,000 per year forever by a company. So this is a non-unrealistic thing, and based on the riskiness of this offer, you think that 5% would be the appropriate discount rate. How much would that be? How much would you be willing to pay for that? So how do we set it up? And it gives you 40,000. Right, pretty simple. So you need to know, for this one, you need to know how much is the payment, what's the appropriate discount rate. Okay. All right. Now, we've been dealing with annuities. They're really useful for a lot of things, and in particular, financial instruments like loans work mostly as annuities. But most of what you guys will be doing sometime in the future, if you're working in a company or in a hospital or a clinical practice, is you'll be working on projects, and those projects very often will not have nice, even cash flows where it's like, we're going to get $1 million a year for 10 years and then it's going to stop, and that's that simple. Life in reality is not that simple. So what we want to deal with are now uneven cash flows. CF for cash flows, uneven cash flows. So let's imagine we have a 5-year contract to build a temporary clinic because some firm, let's say it's I don't know, a mining company, and they plan to mine an area for 5 years, and they come to you and say, Mia, I want you to build us a clinic, take care of our people, and here's the arrangement that we're going to pay you. At the end of 5 years, we're going to shut down. So 1, 2, 3, 4, 5. So in year 1, we'll pay you 200. Year 2, we'll have more people there, so we'll pay you 300. Years 3 and 4, we'll kind of peak out with the number of people that we're going to have. And then in year 5, we're going to be shutting down, so there'll be fewer people, so we'll pay you that much. Now Mia, you've got to go buy all your own stuff to build this thing. So, whatever you can sell it for at the end of that's up to you, right? So you're buying all this equipment and, maybe renting some portable structures and whatnot. And then at the end, so sorry, can you read that? 200, 300, 350, 350, 250. I'm looking at my board. So let me just realize those are kind of mushy together. So Mia estimates that at the end of 5 years, she'd be able to get 200,000 in what we call salvage, right? Which just refers to she's going to sell whatever she bought to set up the clinic to begin with, right? So in reality, that year 5, she's going to get 250,000 in payments from the company. And then she's also going to get $200,000 in salvage. So her year 5 payment is actually going to be 450, right? At least that's her estimate. Okay. And so Mia's doing this evaluation, and she estimates that similar investments yield 7.5% for her. So similar risk investments, she would use a discount rate of 7.5%. So the question is, how much is this worth to her? So how much would she be willing to invest because the company's like, these are the cash flows we're going to give you, right? And she's estimating I'm gonna have to buy a certain amount of equipment. That equipment and other stuff is going to be worth about $200,000 5 years from now. How much would she be willing to pay to set this thing up front in order to make it profitable to her to do it? So what could you do based on what we've already done? This is not going to fit. We're not going to be able to do a TVM on this, right? This is not an annuity because the numbers keep changing every year, right? Well, not every year. There's 2 where they're the same, but the numbers change. So you're not going to be able to do a typical TVM where you're like, okay, N is 5, payment is X, right? Because payment changes. You do know the N is 5. What could you do with what we've done so far? Well, you could value each cash flow individually, right? You could use the present value formula. You could say, all right, PV equals FV divided by 1 plus I to the N. And I could say, all right, cash flow 1 is going to be 200 divided by 1.075 to the first power. Cash flow 2 is going to be 300 divided by 1.075 squared. Cash flow 3 is going to be 350 and so on, right? You could do that. And then what we're doing is we're valuing each one of these individually and bringing them back to the present. We could go all the way out to year 5 where we're doing 450 divided by 1.075 to the 5th power, right? And then we would just add them all up. That would give us the present value of all the cash flows. So that's one option. That would work. That would be accurate. It would be time consuming, right? So there's actually a better way, right? So that is valid. You could do that. We've already done it, so I'm not going to do it, right? The other way you could do this is we can use our calculator has a function for cash flow. So if you can see that on my calculator, it's CF, right? So if you've got that, what we're going to do is feed this information into the calculator. So if I hit CF, right? Sorry, actually, we want to have an investment. Let's assume that the investment would be 1.25 million. So she's asked. So the question actually we're asking, not so much is now, does this make sense given that the investment would be 1.25 million? We could also there's some other ways to do this, but to be simplest with this, we need an upfront investment. So the question is, should she do it if it's going to cost her $1.25 million to start? So CF0, this is called the cash flow register. So if you hit CF, you're going to see, the first thing you should see is CF0. CF0 is the time zero investment. So we're going to put this in as a negative because the calculator needs a negative, right? So our first entry is going to be 1.25 million negative, and then we're going to hit enter, okay? We're still really asking, how much is all this worth? Bring it back, compare it to 1.25 million, right? That's our NPV calculation. So now we're going to arrow down. So you hit enter and then arrow down, and you'll see CO1. CO1 is the first unique cash flow. Well, the first unique cash flow is 200. So we're going to put in 200,000 and hit enter. Okay. And we're going to arrow down again. F1 is asking, F01 is asking, how many times do we get the cash flow of 200,000? And the answer is 1, right? Connor. Uh-huh. No, it's positive. So with a present value calculation, either with the calculator, either the initial investment has to be negative or the payments have to be negative, or the future value, or both, right? So either the present value is negative or the future values, whether that's payments or a lump sum future value in the future, have to be negative. They have to be opposite signs for the calculator to work. Otherwise, you'll get an error. So if you're doing a TVM problem and all of a sudden you're getting an error and you can't figure out why, it's probably because you made both your present value and your future values positive. You forgot to make one of them negative. Okay. That's not the case if you're using formulas. Like if you're doing it by hand and doing formulas, you don't need to do that. But for the calculator, something's got to be negative. Either the present value or the future values have to be. And I'm including, when I say future values, I'm including either the payment numbers, or the future value. And then you'll see next chapter, we'll do both together. So in this case, I am keeping the present value, which is the CF0, that's the amount we're putting in today, as negative, and then the future cash flows, the payments, are going to be positive. Okay, so now I scroll down to FO1. That's the number of times that I get 200,000. Now, if I scroll down again, I get CO2, C02. That is the next unique cash flow. So that's 300,000. And I put in 300, enter, scroll down. FO2 is how many times do you get 300,000? Well, I get it one time. So I'm going to enter 1. I don't even have to enter 1. It's already there, right? Defaults to 1. Then I'm going to scroll down again, CO3. What is the third unique cash flow? Okay, I keep saying unique, right? For a reason. That was one time, 200 was one time, 300 was one time, 350 is 2 times, right? So our next unique cash flow is 350. And it scrolls down. FO3 now is asking, how many times do you get 350? 2, right? So I'm going to enter 2 for FO3, and then I have to hit enter. Did you have a question, or were you just kind of stretching your? Are you hitting enter after you put it in? No, it says enter right here. Right, so I put 2 in, then I hit enter, then I can scroll down. Because if I scroll down without having hit enter, I think it reverts back to 1. All right. So what have my entries been so far? My initial investment of 1.25 million. Cash flow 1 was 200. It happens one time because it's one time. Cash flow 2, CO2 is 300. FO2 is 1 because it happens one time. CO3 is 350. It happens 2 times. So I'm going to have 350, and FO3 tells the calculator then these the following 2 cash flows are 350. So you don't have to keep. It's meant to be a shortcut to help you, because if this was a 20-year cash flow and cash flows 3 through 18 were 350, you'd have to go 350, 350, 350, right, over and over again. So this allows you to say, okay, if it's 3 through 18, that's what, 16 cash flows. So then you just do FO3 is 16, right? So at this point, you're like, that's just confusing, but there's a rationale for it. That is, if you have a really long set of cash flows, it is time saving to do it, Matt. Mm-hmm. So you're saying you're getting 350 twice on that? Like, does it matter if it's back to back? It does matter if it's back to back. Does matter. Okay. Yeah. So you can't have 350 and then something else and then 350 again. It has to be in order, right? So if this was 250 and then it was back up to 350 again, that it has to be in the order that it happens in the timeline. This is where timeline is useful, right? To write out, because it helps you keep track of all the flows. Less so when you have like an annuity. It's helpful to kind of picture it, but it's always the same cash flow every year. Here, when things are changing all the time, it's useful to write it out. Okay. So now we've got FO3 is 2. Hit enter, scroll down. CO4 is now actually year 5. So this is where we start. It gets a little confusing. This is the 4th unique cash flow, right? Even though it's the 5th year. So CO4 is 250 from the company and then 200 from her salvage for a total of 450. And it happens one time. Okay. So these projects are almost always going to have a salvage in them. You're going to, as we move along, we start working more complex projects. You really need to pay attention to that. Is there a salvage value or not? Is there a sale value at the end of this stream of cash flows or not? Because it's very common for students to forget to add the 200 and they wind up with the incorrect year 5 payment, which can make often can make or break a project. Right? That final payment might make you be successful or not. Right. So it's really important to capture it. Okay. So we've got all that in now, and we can scroll back through and look. Right. And you can even edit it if you wanted to. You could change these numbers, which is nice. The cash flow register is a nice little tool. Right. And then CO5, nothing. So we want to ask, I was kind of leaning towards, we want to ask, should Mia do this project? So we have 2 tools that we've worked on so far that we'll keep coming back to. One is net present value, which asks what does net present value ask? Net present value is equal to what? Remember, Faith? No. Okay. You'll do this so many times, it'll just fall out of your mouth without even thinking about it. Yeah. Connor. The present value of the cash flows minus the investment, right? So if we take the present value of all these cash flows and subtract off the investment, we want the net present value to be what? Positive, yeah. It's not net income, but you do want it to be a positive number, right? So you want the present value of the cash flows to be greater than the investment. Otherwise, it's not worth doing, right? If these cash flows that are coming to you sometime in the future, as a result of all the great work you do and the risk you take, do not exceed what you currently have today, then you wouldn't want to do this project, right? So NPV is equal to the present value of the cash flows minus the investment, and we want the NPV to be greater than 0. So in other words, we want these numbers to add up to something bigger than 1.25 million. And these numbers, when they are brought back to the present, we're using 7.5% as our discount rate or our interest rate to evaluate them. And that we'll get into where that number really comes from. But the bigger that number is, the more risk with 2 things. One is opportunity cost. We could invest this money. So if Mia had 1.25 million, she could take that money and invest it in a S&P 500 exchange traded fund, right? A mutual fund. She could just invest it. And she would expect to earn some amount of return on it for the next 5 years, right? Or she could do this project. So we would use whatever so the returns that she would expect to get from whatever other investment she could do with the 1.25 million is her opportunity cost. Right. So we're saying, should I build this clinic or should I just take the money and put it into this other investment? Well, this other investment in this case could yield 7.5% interest. So I don't want to just compare. I don't want to just add these cash flows up and compare them to the investment. I need to discount them by the amount of interest that I would have earned had I just put the money into some other investment, right? So you need to find the appropriate interest rate. For these chapter problems, I'm just going to give you that interest rate. We'll get into later on. We'll get into kind of coming up with the, there's an art to coming up with the appropriate discount rate. But for now, the problems based on this chapter, you're just going to get handed this is the appropriate discount rate. Or you'll say, this is more likely what you'll have is a comparable project would have she would use an interest rate of blah, and that's the number you use, okay? So what's lovely here is with the cash flow register filled in, we can now use the NPV button right here to calculate what the NPV would be. And so the calculator, knowing all these cash flows and knowing the initial investment, will now tell us what the NPV is. The only other thing we have to do is tell it, what is the discount rate? So when I hit the NPV, the first thing I see is this I. So it's asking for my appropriate interest rate or discount rate. So 7.5, enter, scroll down, and it says, okay, the NPV is 0. Well, it's really just waiting for you to hit the compute button. And so the NPV is 52,914. So that is the NPV. That is not the present value of the cash flows, right? That's not this, it's this. So what it's done is, so I need a little more space. So what it's done is it said NPV equals PV of cash flows minus 1.25 million. And it's telling us that the NPV is 52,914. So PV of CF minus 1.250, like so, right? So it's given us the NPV. It's not giving us the present value of the cash flows. So if we wanted to know how much is the present value of the cash flows, what would we do? Sorry? Add the investment to it, right? Because I'm just solving. So I got to add 1.25 million to both sides. So plus 1.25 million tells me that it's no longer the NPV. It is the PV of the cash flows is 1,302,914. Like the TVM, the cash flow register does not clear just because you hit the clear button. It retains that information. Even if you shut your calculator off, when you come back later, the information will still be there. So you have to go through a simpler process of clearing the cash flow register each time you go to use it. Otherwise, it'll retain the old information. So in this case, for example, if we had done a cash flow problem with like 7 cash flows and I didn't clear it, and I went and I typed in my 5 new cash flows, there'd be 2 ghost cash flows sitting out there that would screw up my calculations, right? So you need to clear your cash flow register each time you use it as well. All right, so this tells us that we have an NPV of 52,914. So is this project a go or a no-go? Okay, I'm getting a thumbs up. It's a go. That's correct. It's a go because I want an NPV of greater than 0. 52,000 is in fact greater than 0. What does that interpret that for me? What does that mean for Mia? What was her return? So she has a net present value of 52,000. What does that mean? Yeah, you're in the right ballpark. So I'm really interested in, she exceeded her return on her investment was greater than 7.5%. In order to have a positive net present value, the return on your investment, your ROI, right? Your return on investment, ROI, was greater than the hurdle rate, right? The discount rate that she required for this particular project. So she required 7.5% return. The fact that she has a positive net present value means that she earned more than 7.5% return on her investment. So I just used the phrase hurdle rate. Hurdle rate is kind of the slang that we use to refer to the interest rate that a project has to earn more than, right? So for this project to be, for Mia to want to do this project, she would have had to get a return on investment, an ROI, of greater than 7.5%. Otherwise, she should just take the 1.25 million and put it in that next best investment, right? So we can now figure out really easily what her IRR actually was, right? Last time we did IRR, we talked about the internal rate of return. That's essentially the ROI on the investment. So IRR is called the internal rate of return. We're going to do a couple of different variations on this. This is the simplest one to get. So IRR is roughly the return on investment, or ROI. So you'll hear investors, finance people kicking around, well, what's the ROI, right? What's the return on my investment? And people use it sometimes literally to mean what's the interest rate, sometimes metaphorically, right? If you're talking about like, what's the ROI on an HMP degree? Well, you're not necessarily going to measure that in dollars, right? Or percentages. You'll say, well, it's a quality of life, it's a meaningful career, right? Blah, 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 right? In this case, we're actually talking about a real number. So the IRR, or the internal rate of return, right? We want to have the IRR be greater than the discount rate, which we will refer to as the discount rate or the hurdle rate. Why do I call it the hurdle rate? What's a hurdle? You have to get over it, right? So you're back in, track. Well, Mia does track. You do hurdles? No, they suck, right? Yeah, so you got to run and step over this thing, right? So, the idea, the phrasing hurdle rate means it's a thing you have to get over. So that's kind of a metaphor for I have to get an ROI that's greater than the hurdle rate. So in this case, in this example, the hurdle rate or discount rate is 7.5. So I need an IRR greater than 7.5 to justify doing this project. So the fact that we have an NPV that's greater than 0, we already know that we had an IRR that was greater than 7.5, because the two of them always travel together, right? It's like Leela and Sabrina; they're always together, right? So they travel together. Just teasing you guys, but right. So it's like you have some buddies that always hang together, right? These are the NPV and the IRR hang together. They're always explained. They always are going to tell you the same thing. They just tell it to you in different terms. But if you have a positive NPV, you're always going to have an IRR that exceeds the hurdle rate. If you have a IRR that fails to exceed the hurdle rate, you're going to have a negative NPV. Okay. So how do we get the IRR, you ask? I'm so glad you asked. You hit the IRR button and then you hit compute, and it tells you that the IRR is 8.9%. So all the hard work is putting the data into the cash flow register. Then it's super easy. So in this case, the IRR is 8.9%, which is in fact greater than 7.5%. And so that tells you that this project is also a go, right? So the NPV and the IRR are always going to tell you the same thing. It's just two different ways of finding out, is this a go or no go? All right. Questions about that? We're going to do one. Let you do one. All right, good. So before we before we do the next problem, it all clears, then hit second. And if you're using my calculator, go down to clear work. That will clear your cash flow register. So now if I go to cash flow, yeah. Okay, sorry. Cash flow must be up. So then you hit, there we go. So cash flow's got to be up. So hit CF, the CF button, then hit second, clear work, and it will clear the work. Okay. So you want to make sure that your CF, when you hit CF 0, it's cleared, and then you can scroll down and say, okay, yep, everything's empty. Don't want to start programming something and then have ghost data in there because it'll screw you up. All right. So now we have a project with a 6-year life. $750,000 investment. $100,000 salvage. 10% discount rate. The flows will look like this. Year 1, 100. Year 2, 153, 200, 4, 200, 5, 200, 6, 200. So the flows from the project will be those. So first, make a timeline. Can you read that? 100, 150, 200, 200, 200, 200. So this is not uncommon because a lot of projects have to ramp up. Like that first year might be building up mostly. So let's start by making a timeline. All right, so time 0 gets what cash flow? No. It's your initial investment. Negative 750, right? Year 1 is year 2, year 3, 200, 200, 200. That's 100. So 300, right? Because why is it 300? Because we're getting 200 from the project and 100 from the salvage. So this is really 100 plus 200, so that's 300. And then it's going to be a 10% discount rate. So we usually write the discount rate off to the side. Give you another second to do the calculations. All right, so CF0, we said that time zero is going to be minus 750. 750,000. Now you can do with this, you can drop the zeros. Just remember that you've dropped the zeros. Like I could do 750 instead of 750,000. It will work as long as I don't do 750 and then 100,000, 100,000, 100,000, right? So as long as you're consistent, and then you'll get back an answer, the NPV will also be missing 3 zeros. So you got to be able to bring it back, right? You can do that as long as you remember. So negative 750, hit enter. CO1 is 100. FO1 is 1 because we have one time. CO2 is FO2 is 1. CO3 is FO3 is, oh, watch your timeline. This is where it's useful to have your timeline written out, because this is the period 6 cash flow is the cash flow from the project, but also what's happening at the end of year 6 is you're selling off the equipment or building or whatever it is, and you're getting that cash flow too. So this is really 600 plus 100. That's why I have the 300 here. So FO3 is really 1, 2, 3. I get 200 3 times. CO4 is 300. Did I do? Oh. And it's 1 time, right? Yeah, that was consistent. Okay. So I'm just double checking stuff. All right. So initial investment minus 750,000. Year 1, 100,000. Year 2, 150. Year 3, 200. Year 4, 200. Year 5, 200. Year 6, 300. All right. So now do my NPV. So I hit the NPV button and it says, what's the interest rate? So what's the interest rate? 10%. Enter, scroll down, NPV, compute, 45,268. Is it a go? Yes, because NPV greater than 0. And if you wanted to know what the actual value of the cash flow was at 10%, you would add 750 to this. So it'd be the actual value of the cash flows discounted back at 10% would be 795,268. Right. I'm just adding the 750,000 to the NPV. What about IRR? Does IRR tell us the same thing? Well, yes, by definition, it will. So let's find out what the IRR is. We just hit IRR, compute, and we get IRR equals 11.7%, which is greater than 2%, 10%, which was the hurdle rate, right? So they tell us the same thing. Okay. Good. All right, good. We've got a few more things to do. Now, we're going to go back to our more vanilla annuity calculations, because I want to get into compounding periods of less than a year. Right. So in the problems we've done so far, the payments would come in at the end of the year, and then we would compound the interest based on an annual basis. But in fact, most financial instruments, credit cards, checking accounts, savings accounts, home loans, car loans, do not operate on annual compounding, right? They operate on monthly, quarterly, or In some case, we'll get into bonds operate on a semi-annual basis. So most financial instruments do not operate on a annual compounding cycle. So what do we do with this? Well, let's think about it for a second. We're gonna do that saving for, our down payment again, but instead we're gonna put $500 per quarter into a savings account with an annual percentage rate of 6%. How much would you have in 3 years? All right. So let's draw a little timeline. Time 0, we have nothing. We're going to be investing on a quarterly basis. So first quarter, meaning 3 months from now, we put in 500. Second quarter, halfway through the year, we put in 500. Third quarter, 3/4 of the year, we put in 500. At the 1 year mark, we put in 500. Let me do one more. At the first quarter of the second year, we do 500, so on until we get to 3 years, right? And we put in 500. How many payments are we going to have in total? It's always 500. This is not a, so this is going to be, this is an annuity. So if you can't read my crappy writing here, it's 500. Connor, 12, right? So I'm going to have 3 years times 4 payments per year is going to equal 12, right? Now, the bank is going to pay me. So when you see interest rates listed by financial institutions, they are listed as an annual percentage rate. The way that they actually calculate, so if you have a savings account, those are typically done on they typically compound on a quarterly basis. So what happens is at the end of the quarter, they look at your balance and they give you interest at the end of each quarter. Now, they're not going to give you 6% interest each quarter. What they're going to do is give you a quarter of the 6% interest each quarter. So they're literally going to do 6 divided by 4, 1.5% interest each quarter. So if we are going to do our TVM, because this is a very nice little annuity, right? We have PV, I, N, PMT, FV. So I'm asking you, how much will you have at the end of 3 years, right? So what am I asking you to calculate? I'm asking you to calculate the future value, right? So we don't have anything at the beginning. So PV is 0. So you don't even have to deal with it. You could just ignore it. You could type in PV 0. It won't make any difference. So what we're really asking is, how much is the future value of this stream of cash flows? What is the future value of this annuity? So the interest rate is 6 divided by 4, 1.5. The N is 3 years times 4 payments per year equals 12. And the payment is 500. So then we want to know what the future value is. So we just go back to our calculator. This is a simple TVM problem. So the I is 1.5. The N is 12. The payment is 500. And if we want to have the future value be a positive number, we need to make it negative. Typically, when we are investing, we make the investment flow negative because it's flowing out, right? So the investment flow or the payment is 500. And then we say, okay, what's the FV? I said 3 years, but I meant 6 years. Why did I do that? All right. We can change that later. So the answer is I would have saved $6,521 if I save $500 a quarter for 3 years at an interest rate at an APR of 6%. Okay. Now your calculator is capable of actually changing its setup so that you have compounding periods, different compounding periods, and you would just say, I have 3 years, and it would know, okay, 4 compounding periods per year. I don't do that because I find that I screw that up. And then if you don't go back and change it later, it'll still have 4 compounding periods per year, and then you'll forget and you'll do more calculations, and then you'll be like, I'm getting this incredibly high return, and it's oops, because I still had it programmed to do 4 compounding periods per year when I'm actually doing an annual compounding problem. So I don't recommend doing it. Your calculator is capable of doing that. I don't really recommend it. I would say leave it in the 4-year format. In the full year format, and then do the calculations what I just did. Yes. Yeah. Okay, so I'm going to clear my TVM. My I is 6 divided by 4, 1.5. My N is 3 years times 4 quarters per year, 12. My payment is 500. I'm going to make it negative because it's flowing out. Compute future value. What are you thinking?
I'm thinking, what was the first button that you pressed?
It doesn't matter the order. Okay. So I'm doing it in the order that I have it listed here. So I'm doing, you could do it this way: 6 divided by 4, 1.5 I per Y. 3 times 4 is 12. That's going to be my N. My payment is 500 negative, and then compute FV. Really, the only thing you have to do last is compute the FV. You can do it you can put it in this order. The order doesn't matter as to what you enter the components in. Okay. What if instead of it being 3 years, it was 6 years? What would I change? Same interest rate, but instead of 3 years, I'm going to let it run for 6 years. What would I change? The N. Okay, what would the N be? So then I would just say, okay, N is 24. I is still 1.5. Payment is still minus 500. Compute FV. Whoops. Ah, shit. I cleared it by accident. 24 is my N. 1.5 is my I. 500 is my payment. Compute FV. 14,316, right? Which is nice. So 14,316. If I didn't earn any interest, 500 times 12 is 6,000. So I'm earning $520 in interest, right? Or over 6 years, 500 times 24 is 12,000. I'm earning $2,816 in interest. Right. So, all right. Let's assume the same now. Let's go back to let's assume, let's assume something else. Let's assume monthly deposits and monthly compounding. Let's say $250 per month in deposits with an interest rate of 4%. And we'll do it for 5 years. Try to be consistent. And draw your timeline. 0, 1, 2, 3. So we have, this is monthly compounding. So you could either write 1/12 or you could write month 1, 2, 3, so on. How many months would you have if you're doing 5 years? 60, right? 5 times 12. 5 years times 12 months per year would give me 60. So my N out here would be, then I'd have 250, 250, 250, 250. All right, and I want to know how much money will I have at the end of 5 years. Okay, my payments are minus 250. My I, all right, 4% APR, monthly compounding. What is my monthly interest rate then? Right, 0.3, it's 1/3%. So here's where I would, and this is intentional to do the repeating number there. I would, if I were you, to get the right number, to get the right answer or close answer, when I go to do my I would actually do 4 divided by 12. Right, that way the calculator has 1/3 in it, not 0.33. There's a difference between 0.33 and 0.33 repeating. Right, so to get the calculator to hold that 0.33 repeating, you want to actually do the 4 divided by 12. You get that, hit I, your N is 60, your payment is 250, calculate FV, 16,574. Does that make sense? So you've got to pay attention to get the right I, you've got to say, what was my APR? And then what's my compounding period? All right, so you take, so N is equal to, I rather, is equal to APR divided by number of compounding periods per year. Right, which we sometimes refer to as M as opposed to N. You don't have to necessarily memorize that, but you may see that written that way, right? And then N is number of years times number of compounding periods per year, right? So 5 times 12 compounding periods per year, 12. 5 times 12 is 60. APR 4 divided by 12 compounding periods per year gives me 1/3%. Okay. So let's say that now let's assume that a project will return $1,000 per month for 5 years. Appropriate discount rate is 8%. What is the value of the project? How much would you pay for this project? So it's going to return $1,000 per month for 5 years. The appropriate discount rate is 8%. How much would you pay for this project? What's it worth? What's that stream of cash flows worth? So let's say PV, I, N, PMT, FV. Our little timeline, right? So let's start by saying, what's our N in this case? Connor, how much? Sorry, 5 years. That's probably my handwriting. 60, right? So 12 times 5, 60. So I go 0, 1, 2, 3, 60. Right? My payments are 1,000. Sorry, 1, 1, 1, 1, 1,000. Right? What's my I? Yep, 2/3. So 8 divided by 12 equals 0.66 repeating. And what am I asking you, for PV or FV? I'm asking for PV because I want to know what's it worth today. So that's the PV. So FV is 0, so we're just going to ignore it. Okay. So now we've got enough information to do a TVM calculation. So we've got an I of 0.66. So I'm going to do 8 divided by 12, gives me 0.66 rounded. All right. I'm going to do my N is 60 because 12 times 5 is 60. I've got 60 compounding periods. I'm getting $1,000 per month. We'll go ahead and we'll leave that positive because the idea is that I want to know what my investment is. So payment, compute PV, and I get 49,318, right? Would be the most I would be willing to pay for this stream of cash flows if the discount rate is 8%. Now, if I said, well, the investment's actually going to be $30,000, is this a go? Matt's nodding his head. Why is it a go?
Because you're paying less than it actually is worth.
Right. So the NPV in this case, if the actual investment was $30,000 to set it up, right, then I would have the present value of my cash flows would be 49,318 minus 30,000 would give me 19,318, which is greater than 0. Right? So I have a positive NPV. If I wanted to calculate what the IRR actually was, what would I have to do? So I know that it's got a positive NPV. So I know the IRR is going to be greater than 8%. What would I have to do to figure out what the IRR actually was, assuming a $30,000 investment? What would I have to change here? Well, what am I now solving for instead of PV? I'm no longer solving for PV. I'm solving for no. So I want to know what the IRR is. The IRR is the interest rate that would actually equalize the present value of the cash flows to the initial investment. So in this case, I know the PV is 30,000. Right. I know that I'm telling you the investment to get this set of cash flows is 30,000. So then you know that the PV is 30,000, negative 30,000 for the calculator. The I, N, and PMT, well, the payment's still 1,000. The N is still 60, right? This is a 60-month investment. And then I'm really asking you what the I is that would make the value of these cash flows equal to 30,000. So now I can take that information and say, okay, PV is 30,000, N is 60, payment is 1,000, compute I. It's 2.632. Okay, that's odd. That's weird because if the IRR, that's telling me that the interest rate, the discount rate's 2.632, which is less than 8%. So something's not right. What's not right? Connor, you got an intuition? Sorry? Not divide, multiply by 12. Because that's actually the monthly interest rate, right? 2.632 is the monthly interest rate. So I have to take that 2.632 times 12. The actual return on investment would be 31.58, which is way more than 8%, right? Which is what our NPV told us. The IRR should be more than the NPV, excuse me, should be more than the hurdle rate. All right. So I'm not going to have time to finish the questions on amortization tables. So we'll do that next time. I don't recall if there are amortization problems in the text or not. I do have a couple of minutes, so I am going to finish one last thing. So let's say, so the APR, annual percentage rate, APR is how banks quote their interest rates to you, whether it's for a loan or whether it's for payments on deposits. However, the effective annual rate is often not equal to the APR, the annual percentage rate. So if I quote you a APR of 12%, let's just be simple. So for example, APR equals 12%. And you deposit $1,000 at the beginning of the year, but you have monthly compounding. You would have, if you deposit 1,000 at the beginning of the year, that's a PV of minus 1,000, right? You have an I, N, no payment. We're gonna try to figure out what the FV is. If you just did simple compounding and said, okay, well, 12%, that would be 1,000 times 1.12, I'd have $1,120. And you'd be wrong. That's not how much money you would actually have at the end of the year. Why? Because you have 12 compounding periods. So your interest rate is actually the APR 12 divided by the number of compounding periods 12, so 1%. Your N, because you have 12 compounding periods and 1 year is 1 times 12 or 12. So now we go and plug that in. We say, okay, PV is 1,000, negative. The interest rate is 1. The N is 12. Compute future value. I get 1126. 83 versus 1120. So I get 683 more. So the actual interest rate, the effective annual rate, is greater than what you would expect just based on the APR. How much greater is it? Well, we take 1,126, 82 divided by 1,000, we get 1.1268 minus 1. We have a return of 12.68. So the EAR is actually 12.68%, not 12%. So I'm going to give you a formula for this, and then we'll stop here. The EAR is equal to 1 plus the APR divided by the number of compounding periods, M, raised to the M minus 1. So we had 1 plus, and bear in mind, you have to, in this case, when you're doing formulas, you always have to use the actual decimals, 0.12 divided by 12 raised to the 12th minus 1. So 0.12 divided by 12 plus 1, that's 1.01, 1% per month, raised to the 12th power gives me 11.268 minus 1 gives me 12.68, which is what we just calculated. All right, so banks quote you an APR, but that's not the whole story. If you have a credit card, for example, with a 20% interest rate, your effective annual rate would be 0.2, right? 0.2 divided by 12, because it's going to be monthly compounding. So 0.2 divided by 12 plus 1 raised to the 12th power minus 1. You actually have a effective annual rate of closer to 22%, which doesn't sound like much, but it really adds up over time. All right, let's go ahead and do the homework. Screw it. Now we'll hold off on the homework because I need to do the amortization with you. So we'll do the amortization next time and we'll push into 10. That won't take me long, but it's really important for you to understand because it affects all your, as an individual, it affects your life significantly. So homework will be due, I guess, next Thursday.